Good evening, or afternoon, or morning, whenever you're watching this. Here's a picture of Isaac Newton, and he's reading a book, and an apple fell on him. And then he one day decided, I'm going to try to explain how things move. And this is where physics came in. So, that's exactly what we were studying. We were studying how things moved all year long. We were answering questions like how far does something go, how did it get there, how long did it take to get there. Then we looked at why did it even do any of that in the first place, and those were due to forces. So we know that forces can cause changes in motion. Then we looked specifically how things move, but how things move in circles. So how do things spin? And I think you see where I'm going with this. We're going to look at why do they spin? Why do things even rotate? So, again, as a more laid out, neater form, how is position, velocity, acceleration, and the reason why those things occur are due to forces. And same idea here, but instead of straight lines, we looked at things in circles. We looked at angles, angular velocity, and angular acceleration. The reason why those things happen are due to this thing called torque. And torque you can think of as the rotational version of force. So force around a circle. Let's look at a picture here. Here's a wrench, and we're trying to unscrew this bolt. So if we're trying to unscrew that, we are going to turn it that way. Righty-tighty, lefty-loosey. So we got to turn it this way. So what is this thing called torque? Well, we need to define it in a certain way, but let me show you through an example real quick. So let's compare 2 points. Let's say I apply the same amount of force. I push just as hard in both of those places. You probably realize that if I push more towards the edge with the same amount of force, then I'll probably unscrew the bolt. If I push really close to the middle, it's going to be really difficult. And if you've ever tried this, you know that that's true. So torque depends on 2 things. It depends on, let me erase these really quick, it's getting messy. It depends on the force, and it depends on the radius. So this little symbol here means perpendicular. So perpendicular to what? Perpendicular to the radius. So if I pushed this way on, if I pushed that way on the wrench somehow, I'm not going to turn it at all. So we can't really do anything with that. So it does depend on the direction. And the best direction is making it perpendicular. More formally, our definition is this: force times radius, where this is the radius. So that's the radius of that one. This is the radius of the other one. So same force, different radius, different torque. So let me erase that again. So it does depend on the angle here. So we're going to use this sine of theta to help us get that. Now the angle we're talking about is this angle here, between the force and the radius arm, or in this case it's the wrench. And oops, let me go back here. So what would be different here is, what if I applied a force at some angle like this? Well, you would probably realize that's not going to give you as much torque because the angle is smaller. So the angle is maximized right here when we're at 90 degrees. So if we are at 90 degrees, the sine of that is 1. The sine of anything less than 90 degrees is less than 1. So we are losing torque. So to optimize, we have to go exactly 90 degrees. I want to compare this now to something you've already seen. This is F net equals ma. We've seen a lot of this. So the net force is equal to mass times acceleration. Well, same idea. The net torque is equal to some angular mass times some angular acceleration. Just like this. So, whoa, let me go back. Keep jumping ahead here. So we know that angular acceleration, the Jesus fish, that thing right there, that is angular acceleration, whereas this is linear acceleration. And this m is just mass. It's not really linear, it's just mass. And this I here, that's the weird thing. What in the world is this? How do we find a rotational version of mass? Well, it's formally called the moment of inertia. So if you want to actually look this up outside of this video, you would have to use these words. If you said rotational mass, you might not really get as much, but the formal definition is moment of inertia. And what is it? We still haven't answered what that is. Well, in general, just think that it's just the rotational version of mass. So it has to do, at least it has something to do with kilograms, just like regular old mass. So regular old mass is just mass. It doesn't really get any simpler than that. It's just how many kilograms is this thing? Well, moment of inertia depends on that, and it depends on the shape. That's the important difference, is it depends on a shape. So a rod, a donut, a cylinder, or a solid sphere all have different moments of inertia. So they all resist rotation in different ways. Even if they all had the same mass and the same relative size, the fact that they're different shapes will change their moments of inertia. So every shape has its own unique moment of inertia. Alright, so here's some common ones that you may run into. And I will stress that you do not have to memorize these. These will be things that you are given. Unless you are trying to actually derive these things, which you will probably not have to do much of, or at all, then this is all we need to do. We just need to look these up. So these are listed in tables and in equation sheets and all that stuff. So if we looked at a solid cylinder like this one right here, this would be like a wheel, even though it looks kind of stretched out. It's just a solid cylinder rotating about the middle. And this is how you would calculate the moment of inertia. So it'd be 1/2 times the mass of the whole thing times the radius squared, where the radius is labeled in the picture. And let's look at, let's say we have this. We have a hoop, like a hula hoop, and it rotates about the middle just like the solid cylinder does. Well, it has a different moment of inertia, so it's going to have a different equation. They both have this mr squared term in them, but one of them has 1/2 in front, one of them just has a 1 in front. But we don't write that. So if they had the same mass, they had the same radius, they'd still have different moments of inertia. So let's look at another shape. This is a sphere, a solid sphere, so like a marble or something. Again, it still has this mr squared part, but it has a different number in front. So even if this had the same mass and the same radius, it would still have a different moment of inertia. So it depends on the shape. And again, you don't memorize these. Okay? If you really want to, for fun, you can memorize them. I don't see how that's fun. That just seems awful. So I'm not going to make you do it. So don't memorize them. Don't ask me in class, do I have to memorize these, because you don't have to. These are going to be given to you. Alright, let's summarize this a little bit before we go into an example. And here's torque. We use the symbol tau. It's like a squiggly capital T. And the units are Newton meters. That makes sense because what we have here is a force times a distance. So those are in newtons, those are in meters. Moment of inertia, that's like the angular mass, if you will. And it has the symbol I. And every single one of those terms had mr squared in it. So it has a kilogram times meter squared. So that's the unit we'll use for those. And then lastly, this isn't anything new. That's the angular acceleration. But we want to go into a little bit of depth of how they're all related to each other. So, two ways to calculate torque. We have the moment of inertia times angular acceleration. And remember, this is just a different way to look at this. F net equals MA. So that's just a different way to look at that. And then the last one down here, the force times the radius times the sine of the angle between them, where the angle between them is the angle between F and R. Alright, so let's do an example, but I'm going to do this in a part 2 video, so you don't have one giant video, you have 2 shorter ones. So tune back in for part 2.